Try to picture absolute nothingness. Seriously, shut your eyes and attempt to summon pure emptiness. What appears? Likely a dark expanse, maybe dotted with distant stars if your imagination leans poetic. But at its core, you're seeing a void. You imagine space as a backdrop, a vast empty container where events take place. A planet placed here, a star over there, perhaps an astronaut drifting aimlessly between them. Space itself, in your mind, is just the box that holds everything. It's what's left when nothing else is there. Here's the problem. That box isn't real. The notion of empty space may be the most convincing illusion the human brain has ever invented. The universe isn't a hollow container. It's more like a wobbling mass of gelatin. Not literally dessert-flavored, of course, but in physical terms, you are constantly moving through a substance that bends, compresses, and stretches. When you stare into the air ahead of you, or out into the vacuum beyond Earth, you are not staring into nothingness. You are staring into a field. And if you don't grasp what a field is, then physics will never quite make sense. You'll just be memorizing rules without understanding the game they belong to. So let's begin with something tangible. Picture a large quivering cube of elastic material, a massive block of jello resting on a table. Now imagine reaching in, grabbing a microscopic grain of dirt suspended inside it, and tugging on that point. The gelatin deforms. It stretches and warps. To describe what just happened, it's not enough to say the block moved. That explanation is useless. You must explain how every point inside the cube shifted relative to every other point. That description has a name: strain. Pull on one corner and the center shifts slightly, the far edge barely reacts, and the spot under your fingers moves dramatically. To describe this chaos, you need numbers. Many numbers. At every tiny location inside the gelatin, you must specify how much it stretched sideways, upward, and forward. And it doesn't stop there. You also need to know whether it twisted. Did the top slide one way while the bottom slid the opposite way? That motion is shear. What started as an innocent dessert block has turned into a mathematical monster. A single arrow won't capture what's happening inside it. To fully describe all those stretches and twists, you need a more powerful tool: a tensor, a formidable mathematical object that bundles all these deformations into one structure. Here's the elegant twist. This isn't just about gelatin. This is the operating system of the universe. Physics, at its core, is the act of assigning numbers to points in space. That's the entire job description. If you assign just one number to every point, temperature for example, you've created what's called a scalar field. Picture a chunk of metal that's hot on one end and cold on the other. You could point anywhere inside it and find a specific value waiting there. 20 degrees, move an inch to the left, 25. The temperature doesn't jump randomly. It changes smoothly, forming a continuous terrain. Now imagine connecting every point that shares the same temperature. You'd get invisible surfaces, like contour lines on a map. These are called isotherms. They don't physically exist, but they reveal the shape of heat itself. Still, one number per point isn't enough for the universe's more interesting behavior. Sometimes, space assigns an arrow instead. Think of spinning objects or water flowing down a river. At every location in that river, the water has a speed and a direction. Saying it moves at 5 miles per hour is incomplete. You must say 5 miles per hour downstream. That's a vector field. Look around the room you're in right now. The air appears motionless, but it isn't. Tiny currents snake through it everywhere. If you froze time and attached a small red arrow to every air molecule showing its motion, the room would resemble a porcupine. That forest of arrows is a field. Heat behaves the same way. It doesn't sit still. It travels from hot regions toward cold ones. So layered on top of your temperature map is a second map made of arrows representing heat flow. And there's a simple rule governing them. Heat arrows always point downhill. They flee hot zones as efficiently as possible. Now we need a way to link the temperature values to those arrows. How do we predict the direction heat will move just by looking at the temperature landscape? We apply a mathematical machine known as del, a symbol that acts like a function shredder. Feed it the temperature map, and it spits out a map of arrows. This process is called the gradient, and the name is literal. Imagine standing on a mountainside in total darkness, trying to figure out which way is uphill. You feel around with your feet until you find the steepest slope. That direction is the gradient. The temperature gradient points toward the fastest increase in heat. Go that way if you want it hotter. Heat flow itself simply follows the opposite direction. It slides downhill. But nature doesn't always settle for sliding. Sometimes it prefers to spin. Picture a field of arrows arranged like a whirlpool. They don't radiate outward. They circle around a center. Drop a leaf into that flow, and it won't just drift. It will rotate. To quantify that swirling motion, we use another operation, curl. If the gradient measures steepness, curl measures twist. It captures rotation. Then there's divergence, which tells us how much stuff spreads out or converges. A spray nozzle has high divergence. Water bursts outward. A drain has negative divergence. Water disappears inward. Why talk about slopes, vortices, and drains? Because gradient, curl, and divergence form the grammar of reality. The equations governing light and electricity are sentences written in this language. One of them says the divergence of the electric field equals charge. Translation: electric charge acts like a sprinkler blasting electric field lines outward. Another says the divergence of the magnetic field is zero. Translation: there are no magnetic sprinklers. Magnetic lines never begin or end. They form endless loops. And this brings us to magnetism, where intuition finally breaks down. You think you know magnets. You played with them as a kid. You know they cling to refrigerators and repel each other when flipped. But why does magnetism exist at all? Why does a current-carrying wire suddenly behave like a magnet? Consider the force on a moving charge, known as the Lorentz force. It states that when a charged particle travels through a magnetic field, it gets shoved sideways. Not forward, not backward, but sideways. That's strange. Gravity pulls downward. Electric forces pull inward or push outward. Magnetism nudges you sideways, like an inconsiderate stranger bumping you off course. The usual explanation invokes the right-hand rule. Hold up your hand, point your thumb, curl your fingers, and strike a pose that looks like interpretive dance. It works, but it's arbitrary. Nature has no hands. Here's what's really happening. Magnetism isn't its own phenomenon. It's electricity viewed from motion. Picture a copper wire. Inside it, positive ions sit locked in place while electrons drift through them like a flowing river. That drift is the current. Now imagine a single electron traveling alongside the wire at the same speed as those electrons inside. From the lab's point of view, you see a current. The rulebook says currents create magnetic fields. The field pushes the moving charge toward the wire. Straightforward, but switch perspectives. become the moving charge. From that frame, the electrons in the wire appear stationary since you're moving alongside them. No motion means no current. No current means no magnetic field. So the force should vanish. The charge should drift away. It doesn't. The push remains. Why? Enter Einstein. Motion alters space itself. It contracts. From the moving charge's viewpoint, the positive ions in the wire, once stationary, now rush backward. Their spacing shrinks. They pack closer together. Meanwhile, the electrons appear at rest and spread out slightly. Suddenly, the wire is no longer neutral. It has an excess of positive charge. The force isn't magnetic at all. It's electric attraction. The particle sees a positively charged wire and is pulled toward it. What we call magnetism in the lab is simply electricity reshaped by motion. It's what electric fields look like when relativity gets involved. This loops us back to fields. We describe forces using electric and magnetic vectors, but they aren't separate players. They're the same actor wearing different costumes depending on how fast you run past the stage. Stand still and you see electricity. Move fast and you see a blend of electricity and magnetism. Together, they form a single four-dimensional object, the electromagnetic field. There's a crucial requirement for this to work. Electric charge must be indestructible. Charge conservation isn't optional. You can't create charge from nothing or make it disappear. If charge leaves a box, the amount inside must decrease. Simple bookkeeping. If charge changed with speed, reality would collapse. Heat a metal block and electrons move faster. If their charge depended on speed, the block would become charged just by warming up. Toasters would become lethal. Since they don't, charge must be invariant, unchanged by motion. Now return to magnetic field lines. Their divergence is zero, meaning no magnetic charges exist. Field lines must loop endlessly. Around a straight wire, they form circles. Around a loop of wire, they thread through the center and wrap around the outside like a donut. This structure creates a magnetic dipole. North and south aren't separate entities. They're two sides of the same loop. The lines exit on one side and return on the other. So where do the lines go when they reach the end of a bar magnet? They don't stop. They pass straight through it. A permanent magnet is simply a current loop that never turns off. Inside the iron, countless electrons spin, each forming a tiny loop of current. In iron, these loops align. Their collective motion produces a large-scale magnetic field. There's no mysterious magnetic fluid, just perpetual atomic currents. But these lines and loops are drawings, not reality. They're visualization tools. The true underlying object is something deeper, the vector potential. This is where high school diagrams fail, and we peek beneath the floorboards. The magnetic field turns out to be a shadow cast by something more fundamental. Earlier, we peeled away magnetic field lines and realized they were cartoons. We learned magnetism and electricity are the same thing, seen from different speeds. But to predict what the universe will do next, to understand the machinery itself, we must confront the ghost. We must talk about A. In simple electrostatics, life is easy. You have a scalar potential, voltage. It's like elevation on a map. Know the height everywhere, and the electric field is just the downhill direction. Clean and intuitive. Magnetism refuses to cooperate. It doesn't behave like a slope. It behaves like a whirlpool. So a single number won't work. We need direction. We need a vector potential. Call it A. Think of A as the momentum of space. Picture a river. The water's steady flow is A. Drop a leaf in, and it drifts along. Place a paddle wheel in the river, and it spins. That spin is the magnetic field. The magnetic field B is the curling motion that emerges from variations in A. For decades, physicists dismissed A as a mathematical convenience, a bookkeeping trick. Then quantum mechanics intervened. You can shield a particle from all magnetic fields, hide it behind barriers where B is 0, and the particle still responds. It senses the flow of A. The ghost exists, and it's more fundamental than what it haunts. The vector potential is the bedrock of electromagnetism. The magnetic field is just a derivative, a consequence. Now let's shift perspective. We've been treating fields like misty clouds floating in emptiness. To truly understand the vacuum, stop thinking of it as a cloud. Think of it as a solid. Return to the gelatin. Engineers studying steel, rubber, or concrete use elasticity theory. When physicists analyze empty space, they use the same mathematics. Take that gelatin block again, twist it, compress it. Saying it's under pressure isn't enough. Pressure is uniform. Solids can experience far richer distortions, pulling on one side, twisting another. This internal complexity is captured by the stress tensor. Ignore the intimidating name. A tensor is just a structured collection of numbers. Vector is an arrow. A tensor is something that takes an arrow and transforms it. The stress tensor specifies the force acting on every possible internal surface. It tells you which face is being pushed, which is being pulled. The material responds by deforming. That deformation is strain. Track a dust speck moving from one spot to another, and you get displacement. But strain measures relative motion, how neighbors shift, compress, separate, or rotate. That information lives in the strain tensor. It maps distortion itself. Why bring engineering into cosmology? Because energy doesn't care what medium it inhabits. Compress a spring and you store energy. Shear metal and energy accumulates. The stored energy follows one simple rule: stress multiplied by strain. This holds for rubber bands and for empty space. An electric field is a stress. A magnetic field is a strain. The void between stars is packed with energy, stored in electromagnetic fields, just as energy is stored in twisted steel. That's why light exists. Strike a metal beam and a wave propagates sound. Its speed depends on stiffness and mass density. Disturb the vacuum, and a wave travels there too. We call it light. The speed of light is set by the stiffness and density of space itself. Those constants you see, epsilon naught and mu naught, aren't boring. They are the elastic constants of the vacuum. One measures resistance to electric stress, the other magnetic inertia. Light travels at sea not because of a cosmic speed limit, but because that's the wave speed of the solid medium we mistakenly call nothing. Now for the fun part, real materials fail. Pull a spring too far and it snaps. Stretch chalk and it breaks cleanly across. Chalk is brittle. It can't tolerate tension. But twist that same chalk and it fractures in a spiral at a 45-degree angle. Why? You applied shear, not tension. Yet tensor mathematics reveals the trick. Shear hides tension within it. Twisting creates a line of maximum tension at 45 degrees. The chalk finds that hidden stress and breaks along it. Nature is filled with such concealed mechanisms. The geometry of stress dictates the geometry of failure. So does space itself have a breaking point? Can you strain the vacuum until it tears? Classical physics says no. Quantum electrodynamics says yes. Generate a sufficiently intense electric field and the vacuum ruptures. Particles emerge from nothing, electrons and positrons born from pure stress. Space is not a passive stage. It's a material that can fracture into matter. So return to the original question, what exists between objects? The answer is everything. The quantum vacuum is not empty. It's a plenum, a solid medium filled with fields described by scalars, vectors, and tensors. It has temperature and flow, stiffness and inertia. It carries momentum. It can twist, shear, and store energy. It supports waves. Understanding physics isn't about memorizing that gravity, pulls, or magnets stick. It's about seeing the invisible framework. A differential equation isn't abstract math. It's a set of instructions for how the cosmic gelatin ripples from one point to the next. Einstein didn't invent a new language for gravity. He borrowed the language of engineering. He realized space-time is a deformable solid, and gravity is its strain tensor. So the next time you stare into the night sky, don't see emptiness. Don't imagine a void. See the fields. See tensors stretching and compressing in the dark. See the immense invisible river of vector potential swirling around every wire and every atom. The universe is packed, and the nothing between things is the heaviest thing there is.